Hello and good day everyone. Today we're going to talk about combinational circuits. But first, let's talk about the different type of logic circuits. There are two types of logic circuits. There is combinational logic circuits and sequential logic circuits. Combinational logic circuits, its outputs depends only on its current inputs, and a combinational circuit may contain a number of logic gates and inverters, but no feedback loops. So feedback loops are the connection to from the output to the input. So that is a feedback loop. So a sequential logic circuit has a feedback loop, and the outputs depend on the not only on the current inputs but also on here the past or the output. So here we have 11 differences in combinational and sequential logic circuits. So for combinational logic circuit, we have this, which we talked about earlier, and this is faster, whereas the sequential logic circuit is slower. So it is easier. You'll see later why this is easier, and as we said, there is no feedback loop between the output and the input. For number 5, this is time dependent. Independent, this is time dependent. Now this is time independent since it doesn't have this, you see this clock right here. So for number 6, so for the elementary building blocks, we have logic gates for the combinational circuit, and we have flip-flops. So flip-flops are also made of logic gates, but they are primarily or made of for NAND gates or for NOR gates connected together in a certain pattern. So this uses arithmetic and Boolean expressions, or this is used for arithmetic and Boolean operations, and sequential logic circuit is mainly used for storing data, so that is why they use flip-flops. So here, since this can store data, this can store any state in the data. So again, not clock dependent. So this has no need for triggers. So it's very opposite. So what combinational logic circuit does is opposite to what a sequential logic circuit is. So this have no many memory elements, and this have memory elements, and this is easy while this is not easy. So it's the complete opposite of sequential logic circuit. So here we have the types of combinational logic circuits. So we have arithmetic and logical functions, data transmission, and code inverters. So for arithmetic and logical functions, we have the half adder, subtractors, comparators. So for half adder, as we can see, we have our inputs A and B, and we have the outputs, the sum and the carry. So you can see later how this works when we will use it in a multiplier, why we need to separate the sum and the carry. So for a half adder, this is why it's called a half adder, since it does not what do you call that use the carry. It omits this number here. So for 0 plus 0, we have 0. So the only output is the sum. As for the full adder, we also output its carry. So for example here, half adder, so we have our input 0 and 0. So 0 and, or let's say 1 and 0. So RA is 1 and let's just use this example, 1, 1. So for A and B, we have 1 and 1. So our sum for 1 and 1 should be 1 and 1 is equal to 0 and you carry the 1, so that should be what? 1 and 0 are 10 in decimal. So 10 in decimal is 2, so 1 and 1 is also 2, so that's why it should be written 10. But the output, recorded output is 0 and the carry is, well, not recorded, or, well, it's not recorded, it's, so if we have 1 and 1 here, so 1 and 1, if we put it here, our sum will be 0 and our carry will be 1. So for the full adder, here we have 3 inputs here and we also have sum and carry. So it's almost the same, but yeah, it's almost the same, but the difference is we have 3 inputs here and our sum or our carry is included. You will see later when we use the multiplier circuit. So this is a half subtractor, but instead of a carry, the borrow is used. So 0 minus 0 is still 0, 0 minus 1. Well, then you borrow 1 from the left. So the difference is 1 and you borrowed 1. So you write 1 here. So this is the combinational circuit for the half subtractor. So for the full subtractor, we have also 3 inputs and we have the combinational circuit here. Okay, that's just 1. Okay, full subtractor. Yes, so for next we have our multiplier. So when we say a multiplier, we just say it's like we're multiplying a 2-digit number, for example 10 times 10, so 0 times 0 is 0, 0 times 1 is 1, 0 times, or 1 times 0 is 0, and 1 times 1 is 1, so our sum will be 100, so b0 times a0, here we have here, b0 times a1 here, so it's just like multiplying numbers. So for example here, we have this. So this is the combinational circuit for a multiplier. So we have 4 inputs. We have, for example, 1 0 times 1 0, or in this case, wait, is this 1 0? Yes. Since 2 times 2 is equal to 4, so the output here is 4. So 1 on red, 0 1 0. So let's see if it is correct. So 0 times 0, or 0 and 0 is 0. Or let's just move here, 10. Okay, now our last digit here, which is in this segment here, is directly connected to this. So why is that? Since it is the last digit and you don't have anything to add to here. But if it is this, you add a1 b0, you add a0 to b1 here, so a1 and b0, then you add a0 and b1, a0 and b1, so then you use the half adder. Use the half adder since you still need the carry to add to this one here. So for example, if you have 5 and 6 here, so you have 11, so you have 1 here and you carry 1, so that is what is happening here. There. So same thing with a2 b0, a1 b1, and a0 b2. That is also what is happening. But and you can see it here. So for a2 b2, a2 and b2 here. So you add the carry of this one here, which is here, and you also add the carry of This, hmm, yes, this. So now you get the output. So that is a multiplier. For a comparator, we compare the two datas or the two inputs if A is greater than B or A is less than B or A is equal to B. Now 10 minutes. So for example, A and B. So if A and B is equal, we output 1. For 0 and 1, A is less than B, so the output of our comparator is 0, 1, 0 since mm, this holds true for A is less than B. So for again 1, if A is 1 and B is 1, then they are equal, so we have 0, 0, 1. So this is just the same but more so this is the combinational circuit for this. So we have A, B. We have our conditions here: A greater than B, A less than B, and A plus B. So let's say if we're correct, so we have, for example, we have 1 year and we have 1 year. So if we have 1 year and we have 1 year, then this will light up since A is equal to B. Now for the multiplexer. So a multiplexer is you have many inputs and you only have one output, and you control what the inputs will be using a signal. So for example, you have I0, I1 as our inputs, and we have S as our signal and output here. For example, since we have only two inputs, now we have 0, 1 as our signal. So for example, you have here 0, 0, 0 and 0. So if our signal says 1, then this is 1 here, so the output will be 0. Then again, if we have 1, 0, 0 and 1, if our signal is 0, since this is 0, since our input here at the 0 is 1, then the output will be 1. Same thing here. 1 and 1, and our signal is 0, so this is 0, so the output will also be 1. So this is the combinational circuit for the multiplexer circuit design. Okay, the multiplexer. So the multiplexer works the opposite way. For example, you have 1 and 0 here as our inputs, and you have signal of 0, so this is 0, so the output is 1. See that? The output is 1. So it's just the opposite, but you have input and you have one input and you have multiple outputs. So, but the only problem here is, okay, let's skip. So 1 and 0, now we know what the position of 1 here is, of 1. So the position of 1 here is this, but what if you have 1, 1? Or what if you have the outputs as, the outputs as 1 and 1? In the multiplexer, you have 1 and 1 here, and for 0 you have 1. So what if the output is 1 here? Then you don't really know, since it always outputs 0 on the opposite or on the other signal. So if you have 1 on the other signal, on 0, then you have 0 also. Then you have a 0 on the other. If you have 0 on the one signal here, then you have 0 on Y0. And if you have 1 on the one signal, or on the y1 input, then you have 0. It doesn't know if this is really 0 or 1. So this is the combination circuit of the demultiplexer. So for our encoders, so we have priority encoders and decoders. So the difference between these two is that priority encoders are or okay, let's know what an encoder is first. So an encoder here. So this is a truth table for the encoder. The encoder outputs the value of outputs the value of yes. So for example, you have A, B, C, D, and you have 0, 0, 0, 1. So you have 1 here. So 1 is equal to 2 to the power of 0. So you have 0 here. So you have 0 here. You have 1 and 0, which is 1. 0 and 1, which is 1. Or 1, 2. So only 2 here has high input. So this will be 2. So 2 to the 2 is 4. So 1, 2, 4. So you have a value of 1 here. And you have 1 and 2. So you have 3. So 2 to the power of 3 is 1, 2, 4, 8. So yes, 2 to the power of 3 is 8. 2 to the power of 7 is 1. So what if you have also a 1 here? So that's where the priority encoder comes in, since an encoder will give you an error if this here is 1. So first, this is the combinational circuit of an encoder, and this is the combinational circuit of a priority encoder. It's much simpler and it doesn't cause any problems if you have 1 here. So a priority encoder does not care of the other ones on the right side or on the lower priority bits. So if you have 1 here, it will not care if this is 1, since if this is an encoder, if you have 1 here, then you have 1 plus 2, 3. So what is 3 is equal to 2 to the power of? So that will not be a whole number, so that will be error. So that's what the purpose of priority encoder. Then we have decoders. So it's just the complete opposite of an encoder, and here you have the inputs. You have here 1. So 2 to the power of 0 is 1. Then you have 0 and 1. 2 to the power of 1. So 1, 2. Still the same but opposite. So 0, 0, 0, 1. So this is 1, 2, 4, 8. 2 to the power of 1 plus 2, or 2 to the power of 3. So this is the combinational circuit of a decoder. Okay. Okay. Now we have code converters as our last combinational circuit, type of combinational circuit. So here we have a 3-bit binary to gray code converter. So this is a 3-bit binary. So you have 3 bits. You have 8 combinations. So this is the formula for, or this is the formula for a 3-bit code converter. So this is the combinational circuit, and if you look at the truth table here and use this formula, you get this. So for G2, so for the most significant bit, we won't change this. So for G1, we find the XR of B1 and B2. So XR B1, B2, so still 0, and the XR of B0 and B1 is 0. So for example, let's look at this. So the most significant bit is still the same. So B2 is equal to G2. Then G1 is 0 XR1. So this will be 1, and G0 will be 1 XR1, which is 0. So that is a 3-bit binary code to, or 3-bit binary to gray code converter. So a 4-bit binary to gray code converter is just the same. It's just, well, it's exactly the same. It's just longer. And this is the combinational circuit. So as you can see, you only have two combinational circuits here, or two logic circuits here, or logic gates, and here you have three. So this is the truth table for the 4-bit. So to design a 3-bit gray to binary code, the opposite one of what we discussed first, we use this formula here, or to convert, and this logic circuit here. As you can see, we have our most significant bit still equal, then our B1 equal to G1 XOR B2, G1 XOR B2, so this is 0, and our B0 is G0 XOR B1, so this is also 0. If you input the numbers here, 0, 0, 0, the output here will also be 0, 0, 0. Now, the 4-bit gray to binary code converter is exactly the same, and this is the logic circuit. As you can see, it is longer since it has 4 bits. Now, for the access code, this is much more simpler to remember, since you just add a 3 for a 3-bit binary to access tree code. This is saying access tree, it has the access of 3. The values differ by 3. So for 0, 0, 0, you add 3, so 1, 2, 4, so 1 plus 2 is 3. Then for 1, you add 3, so this will become 1, 2, 4. So for 2, you add 3, then you have 5. So 1 plus 4 equals 5. Then for 3, you add 3, so this will become 6. 2 plus 4, 6. So that's it. Now 4-bit binary is just the same. So that is all. Thank you.